Okay, so this is just a follow-up video to the video talking about heat capacity. So just showing you a little bit about the process of calorimetry, and I'll go through some sample calculations. Calorimetry obviously is the experimental technique that's often used to calculate enthalpies. So let's get started. Coffee cup calorimetry. So this is what this is. And it's a pretty popular one because it's cheap, but also it's pretty accurate, and it's pretty accurate because styrofoam is a good insulator. It has a pretty high specific heat capacity, so it actually insulates well, so the heat transfer that gets recorded in the water, that is the surroundings, by the thermometer is a pretty good reflection of the heat transferred from the system, from the reaction, whatever the reaction may be. So coffee cup calorimetry is pretty popular, certainly in high school chemistry. So we can't not consider the results when we get them from coffee cup calorimetry. The other one, though, is bomb calorimetry. And so this is done more in the lab, and so this is not cheap, but it is accurate and precise for sure. So again, as with most equipment in a lab, there's going to be the possibility to measure to a high level of precision. How a bomb calorimeter works is very similar to a coffee cup calorimeter, it's just a little more high tech. Here in our reaction vessel, we have the system, and so in this case it looks like we might be setting up for a combustion reaction because we have oxygen in the atmosphere, and we have some sample, and we're going to get that reaction going by igniting it. So getting the reaction started, and then that combustion reaction will release heat. And so here we have our water, which is our system. But the system could also be considered to be the container. And so if you know the type of metal that the calorimeter is made out of, you can calculate a specific heat capacity of the container, or you know the specific heat capacity, and so you can put in that component into your calculation, because some of the heat transferred will potentially go into the calorimeter as well as into the water. And so that's the advantage of using a bomb calorimeter made of a known metal of a very high quality. So that's bomb calorimetry. So we're not going to be doing that in the lab, unfortunately. Now, in terms of calculations, there's two equations you need to know. This is one of them. This is an important one, Q equals mc delta T, where Q is the heat that you are calculating as heat being transferred from or to, depending. Mass is the mass of where the heat is transferred from or to. So in a coffee cup calorimeter, that is typically the mass of water. The specific capacity C is then going to be the heat capacity of water. And then a delta T is the temperature change you measure using a thermometer. Delta T is calculated as a T final minus T initial. And if you do it that way, you always end up with a sign. And by a sign I mean positive or negative, depending on the temperature change. And so that sign then can be used and followed through for the subsequent calculations. And if you do that correctly, you always end up with the correct sign for your delta H value, which again, the delta H sign of the delta H tells us whether it's exothermic or endothermic. Now, at this stage in a calorimeter calculation, we do make an assumption, and that assumption is basically that any heat gained, and that's typically going to be heat in an exothermic reaction, for example, that's heat gained by our calorimeter is going to equal heat lost, and that heat lost is going to be the heat that the system produced. And so this is a very common assumption. It's basically an application of the first law of thermodynamics that says energy is not lost, created, or destroyed. It's simply transformed. In this case, it's transformed, and it's also transferred. And so how we see this, so for example, if the heat we've calculated in our surroundings is positive, we then assume that all of that heat came from the system. And so the numbers are the same, but with an opposite sign. And so that is, again, now, remember, we're trying to calculate the enthalpy change in the system, and now we have our negative sign for our system. So this is how we end up going from heat gained by the surroundings to heat lost by the system, subsequently enthalpy change from the system. So don't forget to make that assumption. That's a pretty important assumption in a calculation. Second equation you need to know is delta H equals Q over N. So delta H, again, this is our enthalpy. This is usually what we're looking for. Q, obviously the heat we've just calculated, and so here we want the heat of the system. And N is the number of moles of the system. And so again, we'll see this in play in a minute, but for example, if you have a certain mass of methane, you can convert that to a number of moles of methane, and that is the number of moles you're using here, because the heat lost, or the amount of heat that the methane releases is going to be based on a mass, and that mass we convert to N, number of moles, and now we have an enthalpy in joules per mole. So you have to be able to use that equation as well. All right, well, let's have a look at a few simple examples. So here's a simple one. A tin can calorimeter was calibrated using a small electrical heater. Addition of 1.45 kilojoules of electrical energy raises the temperature of the calorimeter from 21 to 48 degrees C. What is the heat capacity of the calorimeter? So this is just heat capacity, not specific heat capacity. And so there's no equation for that, but it's pretty simple, because we just, if you remember the definition of heat capacity, it was an amount of heat transferred per unit temperature. And so we need an amount of heat, which we have, 1450 joules. Remember, kilojoules to joules multiplied by 1,000. And we need a unit heat. Well, we have a delta T, and that's going to give us a delta T of 26.63. And so we simply look at heat capacity. Remember, heat capacity is uppercase C equals Q divided by delta T. And so 1450 joules divided by 26.63 degrees Celsius equals 54.4 joules per degree Celsius. And so a heat capacity, if you recall, is not dependent on the substance. It is purely dependent on a heat transfer and a temperature change. But we can make it specific to a substance by putting a mass in there. And so now we have the same tin can calorimeter with a mass of 260 grams. And so in this case, we want an application of Q equals MC delta T. But we're asked to find the specific heat capacity, and that's C. So C equals Q divided by M delta T. Well, Q is the same, 1450 joules. Mass now is the mass of our tin can calorimeter, which is 260 grams, multiplied by our delta T, which hasn't changed. It's still 26.63 degrees C. And so when we do the number crunching on that one, we come up with a value of 0.21 joules per gram degrees Celsius. And actually that is the specific capacity for tin. So the reason I want to show this example is twofold. First of all, there's our application of that equation, Q equals MC delta T. We do have to do manipulation, but that's okay. And secondly, we can determine the heat capacity of a calorimeter. And if we can determine that, we can use that in a calculation to give ourselves a higher level of accuracy when we try to calculate a delta H value. Let's go into another one. Okay, so in this case we're using a bomb calorimeter, and so there's not a great deal different here. So let's get started. So here's our 1.922 gram sample of methanol burned in a constant volume calorimeter surrounded by 2 kilograms of water. There's a temperature rise, so delta T is given T. That's kind of nice. Calculate the molar enthalpy of combustion. Now the first thing is we're going to use Q equals MC delta T. Okay. Second thing is we have two masses, so which mass are we using here? Well, you just need to think about it. For example, 1.92 gram sample of methanol. So where's that going to be located? Well, the methanol is going to be right here. The methanol is our fuel or our system. And so in terms of where the energy is transferred to, it's not transferred into here, so that delta T doesn't apply to this. The delta T applies to the water change. And so there's our other mass that we're going to use. Mass of that heat transfer, the heat's transferred into the water, so that's 2 kilograms, which is 2,000 grams. And so because it's being transferred to the water, our surroundings, we use the specific heat capacity of water. And the delta T, as stated, is 4.5, and that's a temperature increase. Water rose, so that's a positive delta T. And so the heat transferred to the water after that reaction is 37,656 joules. So that's the heat transferred to the water. Okay, so remember, we've just calculated the Q for the surroundings. So that's the water. Now remember, we want the Q of the system. So Q system equals negative 37,656 joules. Remember that assumption you make, the principle of heat transfer and 100% heat transfer. So all of the heat generated or transferred to the surroundings came from the system. And so that allows us now to calculate delta H for our reaction. Negative 37,656 joules divided by, well, what is our N value? Well, remember, that is the mass of our system. The mass of the methanol is what we're interested in, so we have to convert that to a number of moles, and that's done for you right here. Just to remind you, given a mass, number of moles equals mass divided by molar mass, 0.05597 moles. And so the molar enthalpy of combustion for methanol is negative 628 kilojoules per mole. So I just converted to kilojoules, make it a slightly smaller number, otherwise it's 628,000 joules per mole. So again, that's one way that you would have to calculate an enthalpy. Let's look at one more. Okay, so in this case we have a mixture. So 100 mils of a sample of potassium nitrate is mixed with 100 mils of a sample of lead 2 iodide in a coffee cup calorimeter. In this case, we're assuming lead iodide is in excess. So that stops it from being a limiting agent problem, which at this stage we don't need. Again, we have a temperature increase, 5.7 degrees was measured, so we know delta T. Calculate the enthalpy of reaction. So again, it's Q equals MC delta T to start with. And again, what's our mass? We don't have any masses given here. We have a volume, concentration, volume. We aren't even given the concentration of the lead 2 iodide, but that's okay because it's in excess. We don't need to know the concentration. But don't forget, this is massive heat transfer to the surroundings, and we need a mass of that surroundings. Well, what is the surroundings? Just have a watch of this quick little video, and hopefully it'll indicate to you how we determine the mass of the surroundings. So as you can see, the mass of the surroundings actually comes from mixing 100 mils of our potassium nitrate with 100 mils of our lead 2 iodide. The reaction that takes place is in those two solutions when they are mixed. There's no reaction before they're mixed, obviously, it's just ions in solution. As soon as you mix them, the reaction can proceed, so our mass is actually 200 grams because it's the mass of the mixture. Where that's the surroundings where the reaction is taking place. That's where the energy being transferred to. That's where we're measuring that temperature change, that temperature increase. The specific heat capacity is of water. again, it's a solution, 200 milliliters of that solution. We can assume that solution is mostly water, and the temperature change, again, positive 5.7 degrees Celsius. It was an increase in temperature. And so when we do that calculation, we get a enthalpy, or a heat of our system, of 400 or 4,800 joules. So grams degrees Celsius divided. So 4,800 joules, and that's positive. So again, Q system is going to be negative 4,800 joules. So we have Q system. We want to find out delta H of our reaction, and that equals Q divided by N. Well, Q is negative 4,800, as we just calculated. Well, what's our N value? Well, it's a solution. We have a volume and a concentration, and we have excess, which we could ignore. So we get our N value from our 100 mils of a 0.3 molar solution. And so there is a calculation for the number moles of our potassium nitrate. And so 0.0300 moles KNO3. And so when we plug that one in, we get negative 160 kilojoules per mole. And so when you mix solutions and the reaction takes place in the solution upon mixing, this is the way you would calculate an enthalpy of reaction. And that concludes this video.